When we have an ionic compound made up of a metal cation and a non-metal anion, it's easy to assign charges to it. So if we saw something like barium chloride, okay, we know that barium has a +2 charge and each chloride has a -1 charge, and there's 2 of them, and so charges are no big deal. I finished this with the last example in a previous lecture with this example of water. This is not an ionic compound. This is a molecular compound. It does not have charges at all in it. What we can talk about with regard to something that's molecular like this, with substances that don't have charges, we can talk about something called an oxidation state. So what we need to be able to do is know what an oxidation state is and how to determine the oxidation states. And it's kind of like a charge, but it's not a true charge, okay? Another name for oxidation state is oxidation number. So they're synonymous terms, synonymous concepts, okay? So even reactions that don't have charges involved and a change in actual charges can still be redox reactions. Here's an example. Sulfur had no charge. Oxygen has no charge. Sulfur dioxide is not an ionic compound. There aren't true charges in there, but this is a redox reaction. It's pretty easy by language to see that sulfur, as it went from on the left to the right, got oxidized. It got oxygen put on it. In its truest sense, it was oxidized. And the oxygen gas is actually therefore reduced in the process. The oxygen gas is the oxidizing agent. It enabled the sulfur to get oxidized. Okay, so there's no ions in this reaction. There's therefore no charge change, but there still is a transfer of electrons in a sense, okay? It's not a complete transfer where something completely takes on electrons, but it's a transfer to the point of sharing. And if you didn't have electrons and now you're sharing electrons, in a sense you are accepting electrons. If the electrons were all yours, but now you're allowing somebody to share your electrons, you are in a sense giving electrons, donating electrons, okay? So you're gain and lose to the point of sharing rather than gaining and lose entirely and saying you can have my electrons, I don't want them, they're all yours. Okay, so what we have to do in order to look at something like this and see what are these oxidation numbers of this, or the oxidation states, is we have a whole series of steps that we have to have. The definition of an oxidation number that we see here is the charge it would have if it didn't just go to sharing, but it completely gave them away. So what would oxygen's charge be in here if it was not sharing, which it is, sharing electrons with the hydrogens, but the oxygen says they're mine, I want them, and the hydrogen says, okay, you've got them, what would the charge be? And that's what an oxidation number or an oxidation state really is. So let us go through the rules one at a time here, and then we'll practice them, okay? Let's kind of just talk through them a little bit, okay? I've already been mentioning this, and students just let go of this and forget it all the time. If it's an element by itself, it has no charge, okay? It will have an oxidation number of 0. So here are several examples. Diatomic molecule H2 has no oxidation number. I mean, it does. It has an oxidation number of 0. If I gave you a piece of aluminum foil, that's the element aluminum. It has an oxidation number of 0. Okay? For our monoatomic ions, so this is an ionic compound made up of barium ions, that's a monoatomic ion, and 2 Cl minuses, those are monoatomic ions. The ions, their charge is its oxidation number. So we would say barium has a +2 oxidation number and each chlorine has a -1 oxidation number. Notice what I said. We define oxidation numbers per atom or per ion, not as a whole. We would not say that this is a -2 oxidation number. It's a -1 oxidation number on each chlorine. Okay? So here I've written the ion Li+, therefore it has a +1 oxidation number. Here I have written the ion S2-, so therefore it has a -2 oxidation number. If I were to write Na2S, Okay, I have two sodiums, they each have a +1, and I have a sulfur 2-. So the sodium has a +1 oxidation number and the sulfur has a -2 oxidation number. All right, so we have elements and we have monoatomic ions. Those are the simplest cases. Next one. Oxidation number of oxygen is almost always as in a compound, not as pure element, because it's a pure element, we already know it's 0. But if oxygen is in a compound, it's almost always -2. There's a few exceptions, and one common exception is in peroxides. Okay, there is an ion of O2 with a 2- charge. It is a polyatomic ion, okay? The oxygens are actually connected together, and overall it carries a 2- charge. So each oxygen would be assigned half of that and would be a -1, okay? There is a molecular compound which is hydrogen peroxide. If you see that, that is a peroxide, so each oxygen is a -1. That's a common exception. You're going to have to be given clues to know you're dealing with this. This is one clue, okay? Or if you saw something like BaO2. Well, you know that barium has to be +2 because it's in the 2A family. So this whole thing has to be a -2, and that's your clue that that is a peroxide. But if you're not given cluers that this has got to be a peroxide, then you could assume, and almost always rightly so, and for this class always rightly so, that the oxygen has a 2- charge. Then there's a rule for hydrogen. Hydrogen is either going to be elemental hydrogen, and we know that's 0, or it's going to have a +1 oxidation number or a -1 oxidation number. How do we know which is which? Well, it'll be a +1 when it's connected to a nonmetal, and it'll be a -1 when it's connected to a metal. So you see two examples here, one in which hydrogen is attached to a nonmetal. My water is an example. Okay, so hydrogen has got to be +1 because it's attached to a nonmetal. Then I see this example of LiH, lithium is a metal. So lithium takes on the positive charge as a metal and leaves the hydrogen as the anion, or the negative charge, or the anion with a -1. So hydrogen it can be positive, it can be negative, and it defines its role by what it's connected to. And you'll have to keep that straight. Next one. Fluorine isn't always. If it's in a compound, fluorine is always -1. Now, fluorine is the first of several halogens on your periodic table, right? The other halogens aren't always. They usually are because they're usually monoatomic ions. But if they are part of a polyatomic ion or part of a compound that is not an ionic compound, then it could take on various charges, and you can only figure them out based upon what they're connected to. So here's fluorine in a compound, therefore it has to be -1. Okay? Chlorine as a monoatomic ion is -1. But here is chlorine inside of a compound, okay? And we're going to see later that it's not a -1, and we're going to see in a little bit how in the world we could figure out what it is. It's actually a +7 oxidation number. All right, now for anything else, those are the rules that we have. For anything else, we have to figure it out based upon what's connected together to what, and knowing that for a molecule, all the oxidation numbers have to add up to 0 because molecules have no overall charge. Or if it's a polyatomic ion, all of the oxidation numbers have to add up to the overall charge of the polyatomic ion. Let me give you an example of a polyatomic ion. Okay? Phosphate. Okay? In order to figure out P, we know that the oxidation numbers of everything in here have to add up together to that 3- charge. So that's what rule number 6 is telling us. Rule number 7 is just a kind of a word of warning. They don't always have to be integers. You don't have to have a +1 or a -1, a +2 or -2. You can have oxidation states that are +1/2, -3/2, that sort of thing. Not common, but it can happen, so don't be thrown by that. So let's practice this together a little bit here, and then we'll continue to practice it in class. We've got our rules, they're handy there, and we're going to go through and determine our oxidation numbers. So let's work on HNO3 first. HNO3. All right, so we go through and we look at rules. Do we have a rule for hydrogen? Well, yes, we do. The rule for hydrogen is that if it's connected to a metal, it's -1. If it's connected to a non-metal, which is more common, it is +1. Well, nitrogen and oxygen are both non-metals, so that would lend me to believe that it is a +1 oxidation number. Now it looks like hydrogen is connected to a nitrogen, and I'm just going to tell you kind of as a side note here that the formula, the way we write it here, doesn't really depict the reality very well. The reality is that the nitrogen has the 3 oxygens around it, like this. Okay, and the hydrogen is actually connected to the oxygen. Not that that matters to solve this problem, because whether you knew it was attached to the nitrogen or you thought it was attached to the oxygen, vice versa. You knew it was attached to the oxygen or you thought it was attached to nitrogen. Either way, those are non-metals, and so that would lend you to know that hydrogen is a +1. Now, do we have a rule for oxygen? Elemental oxygen is 0. This is not elemental oxygen. This is in a compound. And what I told you for oxygen is it's almost always a -2. Unless there's some kind of giveaway within the formula that points that it has to be a peroxide. That's certainly not happening here. There's nothing about, because you don't even know what nitrogen is. So if you're trying to figure out the oxidation number of something else in there, you're going to always be assuming that oxygen is a -2, because that is so much more common. Now, we're going to use the rule that all of these oxidation numbers have to add up to the overall charge of this molecule, which is 0. So I have a hydrogen, and there's one of those, so I'll say 1 times the hydrogen. There are 3 of the oxygens, 3 times a -2, and there's 1 nitrogen, and I don't know its oxidation number, but whatever it is, all of it has to add up to a 0. So I have a +1 and 6 negatives, that's a -5. Plus the nitrogen has to add up to 0. Therefore, the nitrogen has to be a +5, and that's the oxidation number of nitrogen, +5. Now, we can't go to the periodic table and know that nitrogen is +5, and there's not a rule for nitrogen. We have to figure out nitrogen based upon what it's connected to. So let's try this next one. It has nitrogen in it. Is nitrogen always +5? Well, if it was, there'd be a rule for it, okay? But let's see what it is in this compound. NO2 minus. All right, so we have NO2 minus, we have oxygen in there, and we have a rule for oxygen, it's a -2. And then we have to figure out nitrogen, and we know this, whatever nitrogen is, plus the 2 oxygens, which are both -2, have to add up to the overall charge. Well, in this case, the overall charge is not 0, but a -1. So we put a -1 there. So whatever nitrogen is, -4 is equal to a -1, so nitrogen is equal to a +3. So in this case, it has a +3 oxidation number. This is not a true charge. Nitrogen does not have a +3 charge, and oxygen a -2 charge. These are oxidation numbers. These are the charges they would have if they gave their partner the electrons that make up their bond. Okay, so that is nitrogen, and we're seeing 2 different possibilities, and there's other possibilities for nitrogen. It really has a wide variety of oxidation numbers. I want you to stop the video, and I want you to try this one. Determine the oxidation number of sulfur in SF6. Now, to do that, you have to know the oxidation number of fluorine. But stop and work through that and resume once you have it. Well, hopefully you've figured it out that sulfur has a +6 oxidation state. If you came up with +6, pat yourself on the back. It's not an ionic compound, so it doesn't have a true +6 charge, but it has a +6 oxidation number. And if you're like, how did you get that? We have a rule for fluorine. Fluorine is always a -1. There are 6 of the -1s, so sulfur has to be a +6 to make up for it, to make it a neutral compound. Now, what we're going to do in class is practice this a little bit more and make sure we're getting really comfortable with being able to assign oxidation numbers. And when they are molecular compounds like this, we could figure out what's being oxidized, what's being reduced in a reaction. What's the oxidizing agent, what's the reducing reagent in a reaction. Now, I do want to leave you with one last slide here, and this is the most common type of redox reaction. The most common type of redox reaction is a combustion reaction, and we're seeing that here. We use this combustion reaction a lot to heat our homes, to run our stoves, and to run cars. And a combustion reaction just means a reaction with oxygen. Anytime something reacts with oxygen, it's a combustion reaction. And what's going to happen is the oxygen is going to be the oxidizing agent. And it will oxidize an element on the other side. In this case, it's oxidizing the carbon. So we could go through and do oxidation numbers and see this happening here, but I just wanted to leave you with this common reaction. There's no charges in there. There's no cations and anions exchanging charges, but we do have this process as a very, very common type of redox reaction. Okay, that concludes this chapter. That concludes our discussion of this last type of reaction that takes place in aqueous solution. And I guess that's all I have to say about that.